Alright, we're continuing on with our review videos. So far we've covered some of the basic building blocks. We've looked at numbers, right? Real numbers, rational numbers, sets of numbers, including interval notation. Now we're getting into the main characters in a calculus course, which are the functions, right? Everything in calculus has to do with functions of a real variable. So we're going to start simple. We're just going to start out by reminding you kind of what basic function notation looks like, what the definition of a function is, and so on. So how do we define a function? Well, a function starts with two sets, right? So there's a set A, there's a set B, and we often use some letter to define our function. In this case, I'm using f. Okay, so f is my function. So a function from one set to another, a function from A to B, is some sort of rule or a process that allows you to assign every element of your set A to a unique element in the other set B. Okay, and the uniqueness here is key. This is the key part of the definition, right? We're being a little hand wavy on what we mean by rule here, because there's lots of kind of possible what could a rule be? Well, there's lots of options there. The uniqueness is key, right? So if, let's say 2 is an element of my set A, I'm not allowed to assign 2 to two different values, right? There's only going to be one value that corresponds to 2, right? And the way that we indicate this relationship, we use this function notation. So if I want to say that x is associated to y, right, I would say that f of x equals y. This is the kind of common function notation. If you want to specify these sets, you might run into this kind of notation like this. Okay, if you want to specify that f is a function going from A to B, you might see a notation like this, but this notation isn't that common in a calculus course because, as we'll discuss, the sets A and B are always subsets of the real numbers in a calculus course, and we usually don't bother to specify them. Okay, B is usually R, A is some subset of R that we figure out by looking at where our function is defined. So this notation you might encounter in other courses, but probably not in calculus, right? So we just have this relationship here that f of x is equal to y, right? Now, it is possible that you might have more than one x value that's assigned to the same y value. That's fine. Okay, so okay, what would be okay would be something like if f of 1 equals, I don't know, let's say 3, and f of, I don't know, 2/3 equals 3, right? That's fine. There's two different x values that go to the same y value. That's fine. What's not okay would be if f of 1 went to, say, 3, but then it also went to some other value, so like 4 or something, right? So you can't have one x value that goes to two y values, but you could have two x values that go to the same y values. So this is one thing to kind of keep an eye on when you're talking about functions. That if you want to rule out the first possibility as well, this gets into this idea of one-to-one functions, which we might talk about in a later video. So, domain. What is the domain? Well, the domain is basically the set A. Okay. So part of the definition of a function is that it's required to have a value for every element in this set A. And we'll talk about this later in this video, that for the functions that we deal with in calculus, A, well, the kind of default is that A should be the set of all real numbers, but sometimes there are going to be real numbers where the function is not defined, and so then you have to adjust the domain. We'll talk about that in a little bit. The range is the set of all. So this, the set A is all the x values. The range is all the y values. Okay. By the way, I should also mention notation. We sometimes write this as A is equal to the domain of f. You'll see this kind of notation. For range, the range notation looks like this. Range of f. So what is it? Well, it's the set of all values y such that y is equal to f of x for some x in A, if you were going to write it as a set. You could also write this, another way that you could write this is you could write this as simply the set of all values f of x, where x is an element of A. Okay. And the range is, by the way, it's a subset of B. There's no requirement that the function hits every element in B, only that each of these values does belong to B. Okay, so for example, you might have a function that takes on only positive values, and B might be the set of all real numbers, but the range might be only positive real numbers. So that's something that you'll run into. So basic examples, if I have these two sets A and B, right, I can there's lots of ways I could define functions here, right? So here I've got finite sets, and even with finite sets, there are still many options for the for this function. In fact, for each one of these 5 values, I can choose any one of the values in the other set, and I can assign it. So there's 5 times 5 times 5 times 5 times 5 possibilities for how many different functions I could write down, right? I could write down, like a boring example, like everything equals 2, f of 1 equals 2, f of 2 equals 2, f of 3 equals 2, all right? I could do something like that. It's not very interesting, but it works. That's an example of what we might call a constant function. I could mix things up. I could do something like f of 1 equals 6, f of 2 equals 2, f of 3 equals 8, maybe f of 4 equals 10, f of 5 equals, let's say 6 again, something like that, right? So notice that every element of the set A is accounted for. That's required in the definition of the function. Not every element in the set B is accounted for. And one of the ways you might kind of try to picture this is you might say, okay, here's my set A. Here's my set B. So over here I've got 1, 2, 3, 4, 5. Over here I've got 2, 4, 6, 8, 10. And my function is sort of the go-between between these two sets. My function is what's kind of associating elements of one set to the other. So I look here and I say, so 1, 1 goes down here to 6. What about 2? 2 goes across to itself. It goes to 2. 3, 3 goes over to 8. 4 goes down to 10. 5 goes over to 6, right? So 1 and 5 both go to 6, that's fine. That's not ruled out by the definition of the function. The only thing that we couldn't have is we would not be allowed to have like another, if there was another line coming out of 1, if 1 was going to 2 different things, then we'd be in trouble. We wouldn't have a function anymore. But that gives us a basic example of a function, okay? Now, the types of examples that you're used to are in calculus are these ones given by formulas, right? These are the ones you see most often in high school. So things like, f of x equals x squared, right? And here we might say, well, x could be, we could consider any real number, right? So this would be the domain of my function, right? I could consider other domains, but that's probably the one that you would most typically consider for a function like this. I could consider something like an exponential function. I could consider things like like a sine function. We'll be talking about these guys in later videos. These are the types of functions that you are typically going to encounter in a calculus course. And of course, we need ways of understanding these functions, and we'll talk about that as well. How do you understand these functions? Well, you can understand, a little bit by considering some of the values that they take, but you can only consider a finite number of values because we only have so much time, and that doesn't always capture all of the behaviors. So for these types of examples, we typically visualize things graphically, right? We look at graphs rather than looking at tables of values like we did in the previous example where there was only finitely many values to look at, right? What are some more examples? We could look at, the function that takes each student in Math 1560 and assigns them a letter grade. That's a function, right? Nobody's going to get more than one grade. Lots of people will get the same grade. Lots of you will get A's, for example, believe it or not. But there won't be anyone in the class who gets 2 different grades. That I can guarantee. So how do we visualize functions? Well, we've seen a couple of the standard examples, right? One of the examples you sometimes see is that, I don't know, it's sort of a silly thing, but there's this like black box or sort of meat grinder example where there's like an input x, right? And x goes in and then some value y comes out, right? And we don't know what happens inside the machine, but there's a number that goes in and something happens to the number and another number comes out. Okay, that's one picture you often see, right? The other one is like this one I just drew. There's a set A. You have a function that sends the values in A over to the set B. But the most common way that we visualize functions is with graphs, right? So if I give you the function f, I look at all points x comma y, so how do I decide if a point is on the graph? Well, if y happens to be equal to f of x for some x value, right? So for example, with f of x equals x squared, if I plot all those points, so I plot all the points in the Cartesian plane, right? X-axis, y-axis, the way we usually draw this, I get this standard parabola graph. That wasn't a very good parabola at the bottom, was it? Let's smooth that out. There we go. Okay. So we'll be doing lots of graphing in this course. That's going to be the number one way that we visualize our functions. Okay. Now, I promised one comment on domains. So when you're dealing with functions of a real variable, right, the domain is always assumed to be a subset of R. How do we decide what that subset is? Because we usually don't specify it, right? When I say something like f of x equals x squared or e to the x or like this guy, the square root of x squared minus 4, I'm probably not going to tell you a domain ahead of time. It's going to be up to you to figure out what the domain should be. And so the way you figure out what the domain should be is we ask ourselves, well, when or for which x values, when does this make sense? Right? So I look at what I've got and I say, okay, I got a square root function. What do I know about a square root function? Well, we're dealing with real numbers. We're not going anywhere near complex numbers. So if I want to take a square root of something, it can't be negative. We don't talk about square roots of negative numbers in this course. So, can't be negative. So that means what? That means that the answer to my question is that this is going to make sense when x squared minus 4 is bigger than or equal to 0. Okay. Now I've got an inequality to solve. We're going to talk about solving inequalities in a later video. So we'll go over how to do that in a later video. Let's not put the time in now. But let me warn you that you might be tempted here to move the 4 over, take the square root of both sides, and say that x needs to be bigger than or equal to 2. And although that's technically correct, it's only half the answer. There's 2 ways that I can make x squared bigger than 4. I can take x to be bigger than 4, or bigger than 2. Can you think of another way to get x squared bigger than 4? Well, remember that if you square a negative number, that comes out to be positive. So the other option is that x could also be less than or equal to minus 2. So what should be the domain of my function? Well, it should be an interval notation, everything from minus infinity up to and including minus 2, together with, and here's where you might use that union symbol, everything from 2 up to infinity. Okay, so that's it for the basics on functions. In the next few videos, we're going to be looking at special types of functions that you encounter in a calculus course.